Okay, we can continue our discussion of Bessel functions. In this lecture, we'll look at some recurrence relations which follow directly from the series representation of Bessel functions, and how a Bessel function of a certain order is related to the derivative of a of the Bessel function of an adjacent order. Okay, so it turns out that you can relate j nu of x to the derivative of j nu plus 1 of x and the derivative of j nu minus 1 of x. So, and this can be derived directly from the series definition, and using this we can also get some other useful recurrence relations. Basically, it's the same two recurrence relations which, when used in terms of certain convenient linear combinations, give us other forms which have applications in a different context. Okay, so the starting point is of course this series definition of a Bessel function, and now if you take this function and multiply with x to the nu, right, so then we have the denominator here is 2 to the nu plus 2r, but the numerator has become 2 nu plus 2r. Everything else is basically the same. And now we have said, we did not show it explicitly, but it is true that this series is not only convergent, but it's actually uniformly convergent. So if you want to take the derivative of this function, you can do it term by term. So let's take the derivative of this function and carry out term by term differentiation. So if I want to take the derivative of x to the nu times j nu of x, so it's going to be summation r going from 0 to infinity. This stuff constant remains as it is, and so x to the 2 nu plus 2r will give us 2 nu plus 2r times x to the 2 nu plus 2r minus 1. Then we have this factor 1 over 2 to the nu plus 2r as it is, nu plus 2r. Now we can pull out a factor x to the nu outside, right? So nu is independent of r, so I can pull out x to the nu, and then when I look at this series, I have minus 1 to the r divided by r factorial. The denominator, I have nu plus r the whole factorial, which is nu plus r times nu plus r minus 1 the factorial, whole factorial. So this nu plus r will cancel with this nu plus r. There is a 2 here which will cancel with this, and that 2 to the nu plus r will become 2 to the nu plus r minus 1 in the denominator, and I can combine these two and write it as x by 2 to the nu plus 2r minus 1, which is more conveniently written here as nu minus 1 plus 2r, and once again the denominator here has become nu plus r minus 1 factorial, which I am rewriting it as nu minus 1 plus r the whole factorial. The reason I do this is because now this whole series is in suggestive form. All that has changed is from, in comparison with this, is that nu has become nu minus 1. So immediately we can read off from here that the derivative of this object x to the nu times j nu of x is the same as x to the nu times j nu minus 1 of x. Alright, so we have the recurrence relation. It's useful to highlight this and write this as d by dx of x to the nu times j nu of x is equal to x to the nu times j nu minus 1 of x. So we have managed to connect j nu minus 1 of x with the derivative of the higher order Bessel function. So it works in the other direction as well. So let's look at this again, starting from the series expansion for Bessel functions. Suppose we take j nu of x, which we already have, and multiply with x to the minus nu. So now in place of x to the nu plus r times x to the minus nu, so this nu is gone, so we'll be just left with x to the 2r, and the denominator, of course, we have to write it. So we have this expansion for x to the minus nu times j nu of x is summation over r minus 1 to the r divided by r factorial nu plus r factorial times x to the 2r divided by 2 to the nu plus 2r. Now this, once again, we will take a derivative of this whole thing, and then again, because of the uniform convergence, we can take a derivative, perform the differentiation operation on the right hand side by just doing it term by term. So all this stuff remains as it is, and then we get 2r times x to the 2r minus 1, and then you have to multiply with 1 divided by 2 to the nu plus 2r. Now, so we observe that, you know, although here the series started from r equal to 0, here you see that the series is actually going from r equal to 1. The reason is simply that you know, r equal to 0 is just a constant term that's gone. So you can also see that if you put 2r times x to the 2r minus 1 and include r equal to 0, it's okay, and that will go, this 2 times r will give you 0. So it in fact starts from 1. So I mean, rewriting this whole thing, we have minus 1 to the r minus, so this r cancels with this r factorial in the denominator becomes r minus 1 factorial, then we have a new plus r factorial, and then we have x to the 2r minus 1, there is 2 which also cancels with one of these 2's in the denominator, and we have 1 over 2 to the new plus 2r minus 1. And now in fact it's convenient to, you know, introduce a new dummy variable, right? So it says r is being summed from 1 to infinity. Suppose we introduce r minus 1 equal to s, so we would get minus 1 to the s plus 1, well, and then s would go from 0 to infinity, and in place of r minus 1 factorial we'll have s factorial, in place of nu plus r the whole factorial we'll have nu plus s plus 1 factorial, and r will become s plus 1, x to the 2 s plus 1, and then in place of, in the denominator we'll have 2 to the nu plus 2s plus 1. So it's a dummy variable which is getting summed from 0 to infinity, so I might as well just call it r. So it's r going from 0 to infinity, that's this expression I have here. And now I can actually pull out one of these minus 1. So I have minus 1 to the r plus 1, I want to write it as just minus 1 to the r, so I pull out a minus sign, then I pull out this x to the minus nu. So if I pull out x to the minus nu, I'll have an x to the plus nu. So this becomes x to the nu plus 1 plus 2r, but also the denominator there is 2 to the nu plus 1 plus 2r, so I might as well write this as x by 2 the whole power nu plus 1 plus 2r, and then we have, you know, all these factorial constants, everything stays here. And when we look at this expression, we immediately are able to connect it to the expansion for the Bessel function, but now it is for an expansion for a Bessel function of order nu plus 1. So immediately we are able to write down this relation minus x to the minus nu times j nu plus 1. So collecting this, we have the second recurrence relation here, so which is the derivative of x to the minus nu times j nu of x is equal to minus x to the minus nu times j nu plus 1 of x. So we have managed to connect the derivative of a Bessel function to, with respect to its to the Bessel function of the next higher order. So in fact both these relations are, you know, can be written in this way, right? So what we have managed to show is j nu minus 1 of x is 1 over x to the nu times derivative of x to the nu times j nu of x. If I carry out this differentiation, so I can either treat x to the nu as a constant and derive and differentiate with respect to nu, j nu of x. So then there will be a cancellation of x to the nu and x to the nu, so I get d by dx j nu of x, plus if I take a derivative with respect to x to the nu, then I'll get a nu times x to the nu minus 1, and that will cancel with x to the nu in the denominator, and I just have nu by x times j nu of x. So this itself is a useful recurrence relation. And likewise, if I do the same with the other one and, you know, explicitly work out this differentiation, I have j nu plus 1 of x is equal to minus derivative of j nu of x plus nu by x j nu of x. Right? So I have basically the same recurrence relations written in a slightly different way. And once again, it's actually useful to rewrite this in the following way. You can take the sum of these two or the difference of these two. If you take the sum of these two, you see that the first two terms, the first term in the first one and the derivative term in each of these will cancel, and so we are left with just 2 nu by x j nu of x is equal to the sum of these two Bessel functions, j nu minus 1 of x and j nu plus 1 of x is related to j nu of x. If you can just sum these two, it's going to be just 2 nu by x j nu of x. This is also often a useful recurrence relation to use. And again, if you took the difference, it is the derivatives which will survive if you take the difference, and, you know, these terms, the second term here and the second term here will vanish when you're taking the difference, and so we have the result 2 times the derivative of j nu of x is the same as j nu minus 1 of x minus j nu plus 1 of x. Okay, that's all for this lecture. Thank you.